layer 2 access layer. See, basically layer 2 access layer, what does it means? That when we are using layer 2 access layer, what happens? Okay, see, usually what happens at layer 2 in traditional LAN design, we use layer 2 access layer, and layer 3 is my distribution layer. At the layer 3, I am having distribution layer, and at layer 2 I am running access layer. Okay, so the distribution layer is the layer 3 IP gateway for the access layer host. So whenever I am having a switch over here, suppose, and there is a router over here, this is my connection, this is my layer 2, and this is my layer 3. Okay, so for the devices in the layer on the layer 2, this layer 3 will be the gateway, correct? That is the same thing that is written over here. The distribution layer is the layer 3 IP gateway for access layer host. Now whenever possible, what we can do, it is recommended to restrict VLAN for a single access layer switch to eliminate topology loops. Like suppose we are having uh, different switches, like in our diagram, this diagram if I show you, we are having, this is my layer 2 trunk links. Okay, these are my layer 2 trunk links between the distribution layer switches. These are my distribution layer switches, and these are my access layer switches. Okay, so what you can see over here, what we have done, we have VLAN 10 on both the sides. But what happens over here, this switch, when we are working on layer 2, this link will be automatically blocked because of STP. STP is running on layer 2, so it will be automatically blocked. All the links are in layer 3, sorry, layer 2. All the links are of layer 2. Okay, now if we want, suppose if our scenario is like this, in one of the access layer switches we have VLAN 10, other access layer switch is running VLAN 20. Now what we can do, we can have a layer 3 link between both the distribution layer switches so that my data can pass. My data can pass from year to year, layer 3 links. Okay, so I can use some IVR, okay, I can use some IVR routing, correct? So that one VLAN can communicate with another VLAN, and there will be no STP over here. Okay, because we are running the layer 3 links. So figure 1.9 illustrates a loop-free topology where a VLAN is constrained to single switch, as well as a looped topology where a VLAN span multiple access switches. The loop design causes STP block links. Okay, this is my looped design. Restricting VLAN to a single switch provides loop-free design. Restricting VLAN to a single access layer switch, loop-free design, but at the cost of network flexibility, because all hosts within the VLAN are restricted to a single access switch. So what it will do, it will cost me for network flexibility, because if I want to put any user in VLAN 10, I have to go to that physical location of the switch. Okay, some organizations require the same layer 2 VLAN to be extended to multiple access layer switches to accommodate an application or service. So the loop design causes STP to block links, which reduces the bandwidth from the rest of the network and cause slower network convergence. Okay, this is my layer 2 access layer. So basically what happens in layer 2 access layer, we have, what we do, either we can have a loop free topology, one VLAN per access switch, or we can have looped topology with VLAN spanning in the access switches. Okay, like here we can see over here, loop, if we don't block, if STP don't block this link, what will happen, loop will occur over here, loop will occur over here. So that is the reason we need to block one of the redundant link. See how it is connected. See the connection. I have both the access layer switches. This is connected to this switch, and this switch is also connected to this switch. Both are redundant, both are connected to one distribution layer switch only. And these two links are for redundancy, for backup. If one of the link fails, if suppose this link fails, then this link have a connection to this distribution layer switch. Understood?
Yes, understood. It's better.
So with layer 2 access, distribution switches are default gateways for end host. Okay, so distribution, as I told you, layer 3 means layer 3, they are the distribution, they are the default gateways. So we can use first hop redundancy protocol like HSRP, VRRP and GLBP in access, in layer 2 access layer. Okay.
Yes.
Then in layer 3 access layer, what will happen? Now what we are doing over here, routed access is alternative configuration in which layer 3 is extended all the way to the access layer switches. Now what we are doing, we are not making this links as layer 2. We are making this link between access layer and switch layer as layer 3 links. All the links are layer 3 links. So in this design, access switches act as full layer 3 routed nodes, providing both layer 2 and layer 3 switching. And access to distributed layer 2 uplink trunks are replaced with layer 3 point-to-point routed trunks. So what we have done, we have made these links as routed trunks, point-to-point trunks. Okay. Now, when we do this thing, now we don't need first hop redundancy protocol because my layer 2 is running. There is no gateway for my router. Okay, so my layer 2 is running at my layer 2, or you can say at my access layer. I am running routed. I am running routed access. Okay, so no need for first hop redundancy protocol. No STP required. It will increase the uplink utilization, easier troubleshooting, ping trace. Okay, faster convergence will be there. Then, okay, these all are the advantages for having routed access layer. Got it? Okay.
Yes, understood now. Thank you very much.
Yeah, welcome. So now we need to study about switching forwarding architectures. Okay, forwarding architectures. Just give me a moment. So forwarding architectures, we have different forwarding architectures. One is process switching. Okay, process switching is also referred to as software switching or slow path switching. So it is a switching mechanism in which the general purpose CPU on a router is in charge of packet switching. Now there are some types of packets that are required software handling. Okay, so packet sourced or destined to router. Okay, packet that is source or that is having a destination to a router, that is having a need of software switching. Okay, using control traffic or routing protocols. Packets that are too complex for hardware to handle. IP packets with IP options. Packets that require extra information that is not currently known, that is ARP. So these all types of packets need software switching, software handling, you can say. Okay, software handling. Now process switching. Process switching is something like, it is a process in which what will happen over here, the routing table, also known as RIB, routing information base. Okay, routing information base is built from information contained obtained from dynamic routing protocols and directly connected and static routes. The ARP table is built from information obtained from the ARP protocol. So we'll study about this in detail. Process switching. So it is the slowest method that we use. It is the slowest method when a packet is coming, when an incoming packet is coming to the router. What does, how the packet is being processed. So we have control plane and data plane. The control plane is the plane that gives the decision that how the data will be forwarded, and the data plane is the plane that is forwarding the data. Now every packet is examined by the by the CPU, all forwarding decision made in the software. Okay, whenever an incoming packet is coming from a router, the ingress interface means incoming interface will send this packet to CPU. Every packet, each and every packet will go to the CPU at the control plane. The control plane will make the decision whether this, how to forward this packet, on which interface to exit. Okay, what is the exit interface, and these all things. It will be taken care by the CPU. Okay, every packet that is coming will go to, every packet that is coming in the incoming packet will go to the CPU, and the CPU at the control plane or the software at the control plane is making the decision to forward the packet. Okay. Then the packet flow will go to the egress interface, output interface. I'm getting disturbance from someone. Okay, so egress means output interface. Okay, outgoing interface. So here process switching, why it is slow? Because every packet goes to the CPU. CPU will give the decision, then the packet will move outside. This is one type of forwarding mechanism, forwarding architecture you can say. Then another is fast switching or route caching. Now what happened in over here? In the previous, what was happening, that every packet was moving to the, every packet was going to the CPU, and CPU is giving the decision that how to forward the packet. But over here, what is happening? Over here, every packet, every very first packet of any data flow will go to the CPU. Only the first packet of the data flow will go to the CPU, and the CPU will forward that packet, and also it will give the information, forwarding information to the fast cache. There is a fast cache that is created at the data plane. Okay, so the CPU will give the information to the fast cache, you can say route cache information, to the data plane, that if any packet is coming from this data flow, you have to forward it to this egress interface. Only the first packet will go over here, and the first packet will be output from here, and also with the output the CPU will inform the fast cache or the route cache. It will give the information that if you receive the packet from this data flow, send it to this egress interface, or you can say it will give the information that how to forward those data flow. Got it? So only first packet will go to the control plane, rest all the packet will be moving from the fast cache. This is a faster method. First packet in each flow is examined by the CPU, and the forwarding decision cached in hardware for subsequent packet flows. For subsequent packet flows. This is another method of forwarding architecture.
Is that like a specific model that does that, or is
So it is done
is
by
there a way to tell?
all the routers, you can say. There is no specific model, you can say. Nowadays we use CEF, something known as CEF. The older models that were there, they were using some process switching and fast switching mechanisms. Nowadays we use Cisco Express Forwarding, CEF. This is the fastest method. Okay. Hardware forwarding table is created regardless of traffic flows and all packets switch using hardware. So what does the CPU does? CPU will create a hardware forwarding table, and there will be the information FIB information, forwarding information base, and adjacency table will be there. Now the packet will not go to the CPU, it will go to the hardware forwarding table, and all the forwarding decision performed in the hardware table only. Now no need to go to the CPU. Not even the first packet goes to the CPU. All the packets go from the hardware forwarding table, and all the decisions are made by the hardware forwarding table. This is the default switching mode in all the Cisco's router. Okay. CEF is a Cisco proprietary switching mechanism. It is default switching mechanism used by all Cisco platforms that use specialized application specific integrated circuit. Okay. ASIC and network processing unit, NPUs, for high packet throughput, hardware based routing. Okay. Now we have studied two terms over here. We have seen two terms over here, FIB and RIB. We have seen two terms over here. Let me check if I am having any document over here. So we have studied two things, two terms over here. We have seen FIB and previously we have seen RIB. RIB, okay, routing information base. RIB, process switching. So what is FIB and what is RIB? Now these structures within an IP network perform two distinct functions. Okay, so let's take a closer look starting with the FIB only. So the forwarding information base, FIB. Now FIB is also sometimes referred to as CEF table. It is also known as CEF table. Okay, or you can say the IP forwarding table. Now this is used to make IP decision, prefix based switching decision. The FIB, you can it contains the interface number and next hop information. What it contains? Interface number and the next hop information. Like I'll be having over here, I think so. I'm having somewhere over here. See, this is my FIB. FIB. It will be having the prefix based switching decision. Okay, so it will, prefix means network based. Network based slash value based switching mechanism. Okay, so FIB contains interface number and their next hop information. Next hop information. Okay, to reach, you can say, destination network prefix. Now the FIB, as I have mentioned, that in regard to Cisco Express forwarding, is also used in conjunction with CEF. So the FIB itself is a direct copy of routing table. It will be a direct copy of routing table. Now each time a routing change occurs and the routing table is updated, the FIB is also updated. the FIB will be also updated. Okay. Now with CEF, the FIB is used to make IP destination based switching decisions. Now which takes the CPU out of the equation and creates a faster or more, you can say more lightweight switching process. Okay. So one of the things to note about the FIB is that generally speaking, the number of entries found within the FIB may influence the ability of the router to forward the traffic quickly. Now, more the entries there are within the FIB, the longer it could take for route lookup to happen. Now, but these days, what we do, isn't much of an issue with our modern equipment. We have very fast ASIC based forwarding. Okay, that is nearly equal to the line speeds, you can say. Now on Cisco router that have the ability to use distributed CF, or you can say DCF, a copy of FIB would be applied to each of the line card modules. So there is no such issue these days. Okay, so this is another way that the CPU is offloaded in order to increase the amount of traffic that the device can handle without affecting the performance. Okay, so FIB is like your routing table. It has the information about the next hop to reach that network. Okay, to reach that prefix, what is the next hop? Okay, see over here, this is my routing table and this is my what? FIB table. Here is my FIB table and here is my routing table. So routing table is giving me next hop. Here the next hop is same given over here, next hop, and 10.10.10.0 is attached, means is directly connected. Okay. Now comes the RIB. Routing information base. Routing information base is the, you can say, location where all information related to IP routing is stored. Information related to IP routing is stored. That is my RIB. Okay. Now this is not specific to any particular routing protocol, but you can say rather it's used by all protocols such as OSPF and BGP. Now anytime routing protocols learn about a new route, the route is inserted into the RIB. Okay, the route will be inserted into RIB. When a previously learned route comes unreachable, now this route is first marked as unusable and will eventually be moved completely from the RIB if the route remains down. Okay, and the amount of time that it takes for that to happen, that depends upon the routing protocol that's in use. So particular timers that are related to the protocol from which you can say the route was learned. So within the RIB, we will find all the routes that have been learned dynamically through protocols such as OSPF. Okay. Now, this is something my RIB and FIB. FIB and RIB. Now in CEF, we have software switching, software CEF and hardware CEF. Okay, so software CEF is something that is used. Software CEF is also known as software forwarding information base. Now it consists of two things, FIB and adjacency table. Now to read the theory about FIB, the FIB is built directly from the routing table and contains the next hop address. Contains the next hop address for each destination in the network. Now it keeps some mirror image of FIB, forwarding information, contained in the IP routing table. When a routing or topology change occurs in the network, the IP routing table is updated, and these changes are reflected in the FIB as I explained. CEF uses the FIB to make the IP destination prefix based switching decisions. Okay, now adjacency table. What is adjacency table? Adjacency information base, AIB. Now the adjacency table, also known as AIB, contains directly connected next hop IP address and their corresponding next hop MAC addresses. Okay, as well as the exit interface MAC address. The adjacency table is populated with data from the ARP table or other layer 2 protocol tables. Now you can see in the diagram over here, this is my adjacency table and I'm having IP address, next hop, interface and the MAC address of that interface. MAC address. How I got this information? I got this information from my ARP table. And in FIB, I got the information from my routing table. Understood? Now, upon receipt of any IP packet, the FIB entry is checked for a valid entry. If entry is missing, it's a GLIN, adjacency in CEF, which means the packet should go to the CPU because CEF is unable to handle it. Okay, whenever a packet will come, it will go to the, if there is an entry missing in the table, so what it will do in the FIB, the packet will go to the CPU. Valid FIB entries continue processing by checking the adjacency table from each packet destination IP address. Now missing adjacency entries invoke the ARP process. When ARP is resolved, the complete CEF entry can be created. So whenever there is a packet and there is no entry in the FIB, the packet will go to the CPU. Now the CPU will process the data, the ARP request will be generated, and the ARP request, then it will be the when the ARP is resolved, the complete CEF entry can be created. Okay, when the ARP is resolved, it is sent to the software CEF. Understood? Then we have hardware CEF. Now ASIC allows for very high packet rates, but they have limited functionality because they are hardwired to perform specific tasks. The routers have NPUs that are designed to overcome the inflexibility of ASICs. Okay. Now we have two things in hardware CEF. We have ASIC and we have NPUs. ASIC is something which is not very fast. So to make the running fast and to make the things fast, we have something known as NPUs. Packet switching is distributed architecture platforms is done via distributed CEF, DCEF. Okay. Distributed architecture. DCEF is a mechanism in which the CEF data structure are downloaded to forwarding ASIC and the CPU of all line cards so that they can participate in packet switching. This means that switching happens at the distributed level, which increases the packet throughput of the router. So this is not the part of our syllabus, the hardware CEF and all these things. Okay, just we need to know the difference between FIB and RIB and what is the types of this processing mechanism, or you can say forwarding architectures, process switching, fast switching and CEF. So fast switching is sometimes known as route caching. Fast switching is also known as route caching. Okay.
Hello, yes. Can I ask one question?
Yep.
Yeah, so basically, what is the difference between the software safe and the hardware safe? What can we conclude on? What is the difference?
Didn't got your question. Come again.
Okay, yeah, I'm saying that uh, what can be the concrete difference between the software safe and then the hardware safe?
See, software safe is something that works with the software equipments. Okay, like we are having some information in the forwarding base. Okay, we are having a table, we are having a forwarding information base, and on the basis of this forwarding information base and adjacency table, we are forwarding our packets. Hardware is something, it is done with the help of ASIC and NPUs. Now, hardware is something, this is done when you are having distributed architecture platforms. Okay, like you are having some levels and you are having some distributed architecture. So you need DCF over there, distributed. Hardware is not used in our normal forwarding architecture.
Okay, which means that some of the device like switches, they don't have ASIC and the NPU mechanism in them.
This is not about switch. This is about router.
Routers.
So what do you ask?
Okay. No, which means that some of the routers, they don't have ASIC and the NPU mechanism in them. Some have, some don't have. Some those that have are the hardware. What I mean is that
You're getting confused. See, all
uh,
the routers have ASIC and NPUs. There is nothing like they don't have ASIC and NPUs. The thing is that software CEF is used whenever we are having a non-distributed architecture. Non-distributed architecture. Whenever we are having non-distributed architecture and whenever we are having distributed architecture, then we use something known as hardware.
okay, okay, okay.
Okay.
That's fine.
Okay. So this was something about forwarding architectures. Okay. Now we have something known as SSO, stateful switchover. SSO, stateful switchover. Now the stateful switchover is something used for redundancy. It is used for redundancy purposes. Now what will happen over here? I have suppose one route process. Okay. And I have formed a neighborship with that route process. R1 and R2 are forming a neighborship with one route process. Now the main issue is failing over to a backup route process might cause routing protocol neighborship to rest. Now what we have done, we have two route process over here. Now one of the route process, we have formed the neighborship. Now I want that this, whenever this route process goes down, then I need to switch to another route process. Now, as I told you that I have made a neighborship with route process 1. So if my route process 1 goes down, I need to make a neighborship with route process 2. Then I can forward the packets from R1 to R2. Now this is the main issue, that if this neighborship goes down, then I have to switch to route process 2 and I have to form the neighborship between R1 and R2 through the route process 2. Then only my packets will get forwarded. Okay, whenever my secondary packets might be dropped until the forwarding table is rebuilt. Okay, so the issue over here is my packets might get dropped whenever the what do you say, this route process 2 will come up, my packets might get dropped. So what is the solution? The solution over here is SSO. So suppose I have used SSO. So what does SSO will does? What the SSO will do, whatever information it is getting from here, what it will do, it will just forward it to the route process 2 also. It will share the information with route process 2 also. Okay, so that whenever my neighborship, my route process goes down, the route process to have all the informations about the routes. Okay, so config and state information are synced with SSO. Config and state information are synced with SSO whenever my route process 1 is up. But there is one more issue. As my configs are stored, but until my forwarding table is rebuilt, until I rebuild the forwarding table on any of the router, my packets might get dropped. So what can we do? What can we do? So for the first thing, for the first solution, for the first issue, what we did, we used SSO. If my route process 1 goes down, automatically my route process 2 will form the neighborship, but it need to build the routing table. So to build the rebuild the forwarding table, you can say. So to build the forwarding table, it will take some time. So till that time, whatever packets are coming, that packets will get dropped. So what we can do? What we can do for that? So we can consider, you can say, we can make something known as NSF. We can use NSF, non-stop forwarding. Now it will make sure that the routing information maintained by the CEF available in the backup route processor. What it will do, it will make this will be having a CEF. Okay, so whatever CEF it is having, the CEF information will be also passed to this route process too. So in this CEF, we are having all the informations like forwarding informations, FIB and adjacency. FIB and adjacency information is there in this CEF. So this CEF is forwarded to route process 2 at time to time, so that whenever the route process 1 goes down, the other route process 2 will take the charge. Understood? This is known as stateful switchover. Stateful switchover. Understood? Any questions? Okay, let us move to layer 2 now. Now the layer 2 basic thing is my STP. So we have learned STP, why we use STP. So we'll have a quick revision, whatever we have learned at the CCNA level. So STP prevents layer 2 loop. Okay, then it provides redundancy. STP stops loops which occur when you have, you can say, multiple links between the switch. Now STP is an open standard protocol 802.1d. STP is by default enabled on all the Cisco switches. So in this chapter, we'll study about spanning tree protocol fundamentals and rapid spanning tree protocol. So spanning tree fundamentals, you can say spanning tree enables switches to become aware of other switches through the advertisement and receipt of BPDUs, bridge protocol data units. STP operates by selecting a master switch that is known as root bridge and running a tree-based algorithm to identify which redundant ports should not forward traffic. That's what we have learned at the CCNA level. Okay, we have more Now we have some port states that are there in spanning tree. Every port transition through the following states. Okay, the port states are disabled. Disable means the port is in administratively off position, that is shutdown state. Then we have blocking. The switch port is enabled, but the port is not forwarding any traffic. Listening. Now I am assuming you all know these all things, so I am just revising these all things. Listening. The switch port has transition from a blocking state and can now send or receive only BPDU messages. It can only send and receive BPDU messages. That's it. Learning. The switch port can modify the MAC address table, means it will learn the MAC address table. The switch still does not forward any other network traffic beside BPDUs. In the learning, it will learn the MAC addresses. Okay, it will learn the MAC addresses. Then comes forwarding. The switch port can forward all network traffic and can update the MAC address table as expected. Then last one is broken. The switch has detected a problem on a port that can have a major effects. The port discards the packet as long as the problem continues to exit. So this is not a state, you can say it is something like there is some issue with the port. Okay, problem with the port. So we will get this type of state. Now port types that we have learned: STP port types, root port, designated port, and blocking port. Now root port is something, a network port that connects to the root bridge or an upstream switch. In the spanning tree topology, there should be only one root port per VLAN on a switch. So root port, you can say it is the shortest path to reach the root bridge. Okay, via the root port there will be a shortest path to reach the root bridge. Designated port, a network port that receives and forwards BPDU frames to other switches. Designated ports forward connectivity to downstream devices and switches. There should be only one active designated port on a link. On a link. These are my switches. On one link, I can have one port as designated. Another port will be root port or any other port. Another port will be either root port or either it will be blocking port. Any port. But on a single link, only one port will be the designated port. Then blocking port, a network that is not forwarding traffic because of STP calculations. Some key terminologies: root bridge, BPDU, configuration BPDU, TCN topology change notification, and root path cost. So root bridge, the most important switch, all ports are in forwarding state and are categorized as designated port. BPDU, used to identify a hierarchy and notify of changes in the topology. There are two types of BPDU: configuration and topology change notification. Configuration BPDU, used to identify the root bridge, root, designated, and blocking port. Configuration BPDUs are used to identify who is the root bridge, which is the root port, which is the designated port, and which is the blocking port. Topology change notification, or you can say TCN BPDU, is used to communicate changes in the layer 2 topology to other switches. Now if suppose if we are having some switches over here and they are connected with each other in this way. This is my designated port. Suppose this is my root bridge. This is my root ports. Now this is my blocking port, suppose, and this is my designated port. Okay. Now what happens if my this link fails? Okay, there will be a topology change notification. There will be a TCN message, topology change notification, that will be sent. There is a topology change TCN message to the other switches. Okay, so this is something TCN message. Then we have route path cost, the combined cost from a specific path toward the route switch. So the path to reach the route bridge is known as route path cost. Another terminology, some more terminologies. Priority, system priority. System priority is a 4-bit value that indicates the preference for a switch to be route bridge. Now the default values on Cisco switches is for the priority is 32768. System ID extension. This is 12-bit value indicates the VLAN that the BPDU correlates. Route bridge identifier. Route bridge ID. This is a combination of route bridge system MAC address, route bridge system MAC address, system ID extension, and system priority of the route bridge. Okay, route bridge identifier, local route bridge identifier. Now this is a combination of local switch bridge system MAC address, system ID extension, and system priority of the route bridge. Now there are some timers, max age, hello time, and forward delay. Max age, that is maximum length of time that passes before a bridge port saves it BPDU information. Before a bridge saves it BPDU information. The default value is 20 seconds. Hello time, the time that a BPDU is advertised out of port. Every 10 seconds a BPDU message is sent. The default value is 2 seconds, but the value can be changed, can be configured from 1 to 10 seconds. Then comes my forward delay, 15 seconds. The listening and learning state, each 15 seconds. Listening 15 and learning 15. The amount of time that a port stays in listening and learning state. The default is 15 for listening and 15 for learning. Now the Stp path cost. Now these are in the tables, you can see the default Stp path cost. Okay, the route path is found based on the cumulative interface Stp cost to reach the route bridge. Now the interface Stp cost was originally stored as a 16-bit value with a reference of 20 Gbps, gigabit per second. Another method called long mode uses a 32-bit value. Okay, the short method uses 16-bit value. Another method uses 32-bit value and uses a reference speed of 20 Tbps. Now the original method known as short mode is the default mode. This is the short mode is the default mode. So if you are having a link speed of 10 Mbps, then the route path cost will be, the port cost will be 100. 100 Mbps 19. These are something default values. 1 gigabits 4, 10 gigabits 2, 20 gigabits 1, 100 1 TB 1 TB 1, 10 TB 1. Okay, so these all are 111 and these are changing over here. It depends on the link speed. Now here in this diagram, switch 1 has identified as the route bridge and the route port and designated and blocking port has been identified in this topology. Now the first step is route bridge election. Okay, how the route bridge is elected? How the route bridge is elected? The first step that we need to do to identify the route bridge, as a switch initializes, it assumes that it is the route bridge and uses the local bridge identifier as the route bridge identifier. Whenever a switch reboots or it initializes or it starts. Now It then listens to its neighbor's configuration BPDU and does the following things. Now suppose we are having 3 switches. Okay, suppose we are having 3 switches over here. And these switches are connected with each other. Now whenever switches reboot, as we have seen, whenever the switch is rebooted or whenever the switch starts, it will assume that I am the root bridge. What it will assume? That I am the root bridge. Okay. Then if it listens the neighbor's configuration BPDU and does the following thing. If the neighbor's configuration BPDU is inferior to its own, the switch ignores that BPDU. Okay, inferior. If the neighbor's configuration BPDU is preferred to its own BPDU, the switch updates its BPDU to include the new root bridge identifier along with the new root path cost that correlates the total path cost to reach the new root bridge. Now the process will continue until all switches in the topology have identified the root bridge switch. STP prefers lower priority number, then goes to the lower MAC address. Okay, so what the switch will do? Switch will consider, suppose switch 1 is considering that I am the root bridge, and then it listens the configuration BPDUs from all the other switches. Okay, now what happens over here? Suppose I'll give that 32768 is the priority on all the switches. 32768. 32768. Now 32768 is the priority on all the switches. This is the default priority. Now the priority is having a tie. Okay, so what it will do, it will look for the MAC address. Suppose my switch 1 is having a MAC address of 01, this is having a MAC address of 02, this is having a MAC address of 03. Now it will see if it is inferior, less than, if it is not a better, if it is not the lowest value of the other switches, then what the switch will do, it will ignore them. It will ignore them, and what in this scenario, these are having some inferior BPDUs. These two switches are having some inferior BPDUs. So the switch 1 will ignore and it will make itself as root bridge. Okay, because I am having the lowest bridge ID. Lowest bridge ID. If the priority, see, what is the criteria to select the root bridge? The bridge ID with the lowest, the bridge with the lowest bridge ID will be elected as the root bridge. And bridge ID consists of priority plus MAC. Bridge IDs consist of priority plus MAC. Now priority is same on all the Cisco switches 32768. Then next thing it will consider, if priority has a tie, it will consider lowest MAC address switch. So in our diagram, the lowest MAC address switch is 01 and it is switch 1. So switch 1 became the root bridge. Then the second thing that we need to consider is my root port. My root port. Which will be my root port? Criteria to elect the root port. Okay, or STP root path cost. Now in this diagram, if I see the STP root path cost, the advertised root path cost is always the value calculated on the local switch. Now the local root path cost is the advertised root path cost plus the local interface port cost. Okay, so in the figure it illustrates that root path cost as switch 1 advertises the configuration BPDU towards switch 3 and switch 3 towards switch 5. Okay, so my configuration BPD, my root path cost on switch 3 will be something 4, and switch 4 is having to reach the to reach this switch, it is having 4. Okay, it is having the root path cost as 4. So from switch 5, what is the root path cost to reach the root bridge? The root path cost to reach the root bridge is 8 over here now. 4 means I am having how many? What is the link speed? 1 Gbps. 4 means I am having 1 Gbps link. So to elect the root port, root path cost, we have seen root path cost is something 4 over here, root port interface cost. On this, the root port interface cost is 4 because I am having 1 gigabits as my link speed. And over here also this root port is having a cost of 4. So 4 plus 4 is 8. To elect the root port, we have different criterias. First, we can check. First criteria is lowest cost to reach the root bridge. Lowest root path cost. Now suppose here I am having the cost as 4 on all the links. On all the links I am having cost as 4. Now what the switch 2 will check, I am having 2 ports. Now among these 2 ports, which will become the root port? So what is the lowest cost? I can reach the root bridge from here also, from here also. So if I go via router 3, the cost will be 8. If I go via router directly, the cost will be 4. So what it will do? It will make this port as my root port. Lowest root path cost. Lowest root path cost. Okay, same thing will be done by R3, and this will become my root port. This will become my root port. Okay, now the second criteria, lowest. Now if suppose we are having some scenario like who are studied the CCNA from me, they know the scenario over here. Like I am having a switch over here and the switch is having some links connected. Suppose the switch is having 2 links connected over here and also 1 link is connected over here. Okay, now the cost of all the links are same, 4, 4, 4. Now which switch I have to select? First I have to select one switch. Either I can go via 2 or either I can go via 3. So how to select which port will be my root port? So to select, the first criteria is lowest root path cost. Okay, the first criteria says lowest cost to reach the root bridge, that is lowest root path cost. So I will calculate. If I go via switch 3, 4 plus 4, 8 via switch 3. If I go via switch 2, any of the link, 4 plus 4, 8. Now both of the switches are having the same root path cost. Now what? Now what we need to consider? Now we need to consider the lowest sender's bridge ID. So who is giving me the information? These 2 switches are giving me the information about the root bridge. Okay, and who is having the lowest bridge ID among these 2? 2 and 3. Who is having the lowest bridge ID?
2.
2 is having the lowest bridge ID. 2 is
2.
having the lowest bridge ID.
Yeah, 2.
So what I will do, I'll make this link as blocking link. I'll make this link as blocking link. And now I will select this. Okay, I will forward it from switch 2. Okay, now I have 2 links over here and both the links are having same root path cost. Now what I need to do? So first criteria, lowest root path cost. Second criteria, I have done the second criteria also. Now there is third condition that I am having two links from the connected to the same sender bridge. So what it will be taken? So there are two things that can be considered over here. The first thing is port priority, something known as port priority. Port priority. Now default port priority on all the Cisco switches is 128. Default port priority on all the Cisco switches is 128. Now our priority is also having a tie. Now what I have to do? The third condition, port priority, is also not fulfilling, or it is not giving me the root port. So I'll come to the fourth condition that says you have to select the lowest sender's port. Lowest sender's port ID. So suppose this is connected to port number 1, this is connected to port number 2, this is connected to port number 2, and this is connected to port number 1. Now which link will be selected? This is my suppose link number 1 and this is my link number 2. Which link will be selected as per this condition? Lowest sender's port ID.
1.
Link number 1 will be selected, correct? So this port will become my root port now, and this port will be in the blocking state. Understood? This is my criteria to elect root port in different conditions. All the ports of root bridge are designated ports. Okay, so this is something we have already studied at the CCNA level. Now criteria to elect designated and blocking port. Now root port have been identified and all other ports are considered designated ports if two non-root switches are connected to each other on their designated ports. One port must be set to blocking state to prevent the forwarding loop. Calculate which port should be blocked between the two non-root switches. So how it will be calculated? Lowest root path cost. Okay, how it will be calculated? Suppose let me consider only 3 switches in this scenario. Okay, don't consider the 4th switch. So I'll just remove the 4th switch over here. There is no switch over here. Now we are having only 3 switches over here, and what it is saying me, it is saying that consider the lowest root path cost. Now this is my direct link and this is my indirect link on R3. This is my direct link on R2, or you can say switch 2, and this is my indirect link. If my direct link fails, I have the backup. So what it is saying me, it is saying me the first criteria is lowest root path cost, the lowest cost from alternate link. The lowest cost from alternate link. So if I am on switch 2, if I use the alternate link, the cost will be 4 plus 4, 8. And if I use R3, the cost will be 8. Now on both the switches, the cost is same of the alternate link. If the cost is same, then I have to go to another criteria, lowest sender's bridge ID. Now among these two switches, who is having the lowest bridge ID? Switch 2 is having the lowest bridge ID, 02. So this will become my designated port and this will become my blocking port. Understood? Any questions, guys? Any questions? Okay. Stp topology changes. Now there might be some situation that Stp topology will get changed. Okay, topology changes might occur. So topology changes in the sense BPD, like one of the link fails. Suppose one of the link fails. Okay, so the topology will change. So what will happen when the topology will change? So BPDU always flow from the root bridge toward the edge switches unless there are changes in the topology. Unless there are changes in the topology. Now the switch that detects a link status change sends a topology change notification BPDU toward the root bridge out of its root port. So whatever switch that detects that the link status has been changed, the switch will send a TCN BPDU to the root bridge. If an upstream switch receives the TCN, it sends out an acknowledgement and forwards the TCN out its root port to the root bridge. Okay, if we are having layered structure like this, like if this switch is sending to this switch, then this switch will send to the root bridge. Okay, upstream switch means this switch. Upon receipt of TCN, the root bridge creates a new configuration BPDU with the topology change flag set, and it is then flooded to all the switches. Okay, who will create the configuration BPDU now? The root bridge. When switches receive this, they set their MAC address timer to the default 15 seconds. Then the device flushes its MAC address table if it has not learned from a device in the last 15 seconds. Okay, so this is some of the process that it goes on. We will see with the example over here. Okay, so suppose this is my topology and my link between switch 1 and switch 3 goes down. The direct link between the switch 3 and switch 1 goes down. Switch 1 is my root bridge. Okay, like we have seen in the example in the paint, we have seen. So this is the same scenario. Once there is a topology change, then what will happen? Switch 1 detects the link failure on its gigabit 1/0/3 interface. Switch 3 detects a link failure on its gigabit 1/0/1 interface. See, this is my made, my handmade presentation. So that is the reason I'm just going and explaining you with this presentation only. Okay, because there is no configuration part over here, so we have to study with this presentation only. In later lectures we'll be doing configurations also when we'll be starting about STP more. Okay, so when switch 1 detects the link failure on its and switch 3 detects on its this interface. Now normally switch 1 would generate TCN flag out of its root port, but it is a root bridge, so it does not. Switch 1 would advertise TCN if it were not a root bridge. Okay, now switch 1 will not advertise the TCN message because it is a root bridge. Switch 3 removes its best BPDU received from switch 1 on gigabit 1/0 interface because it is now in down state. Okay, what it will do, that this is the best path. So what it will do, it will remove this best BPDU. Okay, and it will say at this point switch 2 would attempt to send TCN toward the root switch to notify a topology change. Okay, see, it is sending a topology change notification, but the link is down, so it is not able to send the topology change notification. Then what will happen? In the third step, switch 1 advertises a configuration BPDU with topology change flag out of all its port. This BPDU is received and relayed to all switches in the environment. Okay, so it will come to this switch because it cannot come over here because switch 1 knows this is down. Okay, switch 1 does not need to send a TCN message in it because it is a root bridge. Okay, so switch 2 and switch 3 receives the configuration BPDU with the topology change flag. These switches then reduce the MAC address age timer to the forward delay timer to flush out the old MAC address entries. Now in phase 2, switch 2 does not know what changed in the topology. Switch 3 must wait until it hears from the root bridge again, or the max edge timer expires before it can reset the port state and start listening to the BPDUs on another interface. Okay, making this port into forwarding state, or you can say not forwarding state, listening state and learning state. It will move it to the listening. Before moving it to listening and learning state, what do you need to do? It need to hear something from, either it will hear something from the root bridge, or the max age timer gets expired. If the max age timer gets expired, then it will reset its MAC address table, and it will start. See, it will switch 3 waits the max age timer before it can restart the STP port state, listening 15 seconds and then learning 15 seconds. So it will wait, okay, in the blocking state only. It will wait in the blocking state, but after 15 seconds, what will happen? It will start forwarding the or listening the packets from here, from on this interface. Okay, it will start listening and learning from this interface if my direct link fails between switch 1 and switch 3. The same thing will happen if my direct link fails between switch 1 and switch 2. If my direct link fails between switch 1 and switch 2, the same thing will happen. Okay, the same configuration, the same process will happen again. See, switch 1 detects the failure on this interface, then switch 2 detects the failure on the interface. I have missed out something, I think so. The same process will happen over here in this. If my direct link fails, both are my direct links. Direct links to the root bridge. Both are my direct links to the root bridge. Correct? Both are my direct link to the root bridge. Now the next thing is if my indirect link fails. What if my indirect link fails? Now on switch 3, indirect link fails. STP communication between switches is impaired or filtered while the network link remains up. This situation is known as indirect link failure, and the timers are required to detect the remediate topology. Now, what if this indirect link fails on switch 2? If this is my direct link and this is my indirect link on switch 2, and on switch 3 this is my direct link and this is my indirect link. If my indirect link fails, then what is the scenario? Now there is an impedant or data corruption on the link between switch 1 and switch 3. Now there is something that the link is up but the data is impaired, or the data is corrupted, you can say. So an event occurs that impairs or corrupts data on the link. Switch 1 and switch 3 still report a link up condition. See, the link is up, but what it is showing me? It is showing me that there is a corruption in the data. So switch 3 stopped receiving the configuration BPDUs. Okay, whenever there is a corrupt data, then the switch 3 will not receive the configuration BPDUs on its root port. Now it keeps a cached entry for the root port on gigabit 1/0/1, this interface. Configuration BPDUs from switch 1 that are being transmitted via switch 2 are discarded. These are discarded. So see, this is getting, this switch is sending the configuration BPDUs both side. Now this configuration BPDU is sent over here, and this switch 3 is discarding that because it is in the blocking state. So now once the max age timers expire on the switch 3, the switch 3 flush the cache entry on the root port. Switch 3 transition gigabit 1/0/2 from the blocking to listening state. What it will do, once the max age timer expires, it will block, it will make that link to, so max age timer is for 20 seconds. Okay, so how much time it is taking? 20 seconds. Then to come up, 15 plus 15. It will take 50 seconds for the, if my indirect link come up, it will take 50 seconds for my this blocking port to come up. Switch 2 continues to advertise the BPDUs from switch 1 towards switch 3. Switch 3 receives switch 1's configuration BPDU via switch 2 on this interface. This port is now marked as root port, and it is removed from blocking port, and it is marked at root port because this is my direct link and it is failed, and continues to transition through the listening and learning state. The total time it takes for reconvergence is about 52 seconds. Okay, so in real time it takes 52 seconds, but we give the time as 50 seconds only. We say the time as 50 seconds only. Okay, now we have something like optimizing spanning tree. Optimizing spanning tree. So to optimize spanning tree, we have something known as BPDU guard, BPDU filter, root guard, unidirectional link failure. Before going through this, we'll see something known as tuning STP. How to tune our STP. What all things we can do. What all things we can change, you can say. So first of all, we'll see something practical on packet tracer, which will give me the idea. Now I have some switches. I'll take some switches over here. Now when I connect these switches, they will run spanning tree protocol. The switches are running spanning tree protocol. You can see the amber color. Okay, the amber color indicates that they are running spanning tree protocol. Like if I want to verify, I can go in the CLI and you can check. I can go in the CLI, I can check show enable show spanning tree. So it came into forwarding state. Okay, see now this is in the blocking state, means this is my root bridge. This is my root bridge. All both the ports are in designated forwarding. Okay, this will be my root bridge. So now tuning STP means changing the timers. Okay, changing, you can say, the priority value, changing the modify the cost. Okay, the cost of the interface, or to change the port priority. We can do anything. We can tune our STP. Let this transition get complete. Translate. Enable show spanning tree. If I see show spanning tree over here, you can see this bridge is the root bridge. Okay, because it is having the lowest MAC address. Okay, this bridge is the root bridge. So this is the root bridge. Both the ports are in forwarding state. The cost is 19 over here, and the port priority is 128. This is a point-to-point link. Okay, now I told you that if my direct link goes down, suppose I am on switch 2, and if my direct link, that is my fast Ethernet 0/1 goes down, okay, interface fast Ethernet 0/1, I'll say shut down. It is in the blocking state. The alternate link is in the blocking state. Now it came into listening, then it will go into learning. 15 seconds of listening, then 15 seconds for learning. Now it came into learning state, then it will go into forwarding state. Forwarding state. Okay, so now I'll go and I'll make the link up again. No shut. Once I make the link up again, this link went into the blocking state again. But what if I am on the switch that is having the blocking port? So if I am on a switch that is having a blocking port, this is my direct link and this is my indirect link. So if my direct link fails, interface fast Ethernet 0/1 on the switch that is having a blocking port. On the switch that is having a blocking port, if my direct link fails, this is my direct link, then how much time it will take for this link to come up? So let us check. Shut down. Show spanning tree. See, directly it went into listening state. It will not wait 20 seconds in the listening and learning. It will not wait 20 seconds in the blocking state. It will directly move to listening, 15 for listening and 15 for learning. So if my direct link fails on my switch that is having a blocking port, then the alternate link will come up in 30 seconds. And if my indirect link fails, then the alternate link will come. If my direct link fails, then it will come up in the 30 seconds. But on the switch which is not having the blocking port, if my direct link fails, then the alternate link will come up in 50 seconds. Understood? Getting me or not? Okay. Now suppose we are having two switches, one switch and two switch, and both the switches are connected with two links. Okay, two links between them. So let the spanning tree get completed. Okay, now my switch 4 is having a blocking port. Okay, switch 4 is having a blocking port. It means the switch 3 is my root bridge. So to check show spanning tree for VLAN 1, I'm only having one VLAN. So show spanning tree for VLAN 1. So I can see this bridge is the root bridge. This bridge is the root bridge. Okay, and the interface, it is having a cost of 19. Now I want, suppose I want that my I'll configure switch. I've configured uh, switch 3 and switch 4. Now I want that switch 4 should become the root bridge. What I need to do? I can do it with different things. I can change the priority value. If I change the priority value, then the root bridge will become the switch 4 will become the root bridge. Correct? If I change the priority value. So to change the priority value, what command I have to give? So by default, in all the cases, by default in my case, the switch 3 is my root bridge. I want that switch 4 should become the root bridge. Okay, so both the switches are having the same priority value. Okay, both the switches are having the same priority value. I want that switch 1 should become the switch 4 should become the root bridge for VLAN 1. So what I can do, I can change the priority value. What I can do, I can change the priority value. So how to change the priority value? Spanning tree VLAN 1. Either I can say priority 40, any priority 4094, suppose I give 4096. 4096. Okay, the priority I gave is 4096. Once I change the priority, you can see the switches are running on that link. The switch are running on a link. The switch is running the spanning tree protocol again. Show spanning tree. This bridge is the root bridge. My switch number 4 became the root bridge now. How? Because I changed the priority of the root bridge. Okay, see 4097 is the priority, but my switch 3 is still having the priority as 32768. Correct? So this way we can change the priority. I can change the port cost also. So to change the port cost, I need to go inside the cost, fast Ethernet 0/1 suppose, and I'll say spanning tree cost. I can give any cost between 1 to, so I'll give a cost as 4. So here it is not changing. Spanning tree cost is 4. Okay. Okay, I have to go on the other side of other switch also. Interface Ethernet 0/1. Spanning tree cost is 4. The cost is not getting changed over here. But the command is same. You can try it in GNS3. Okay, might be possible. This is the show spanning tree for VLAN 1. It is not getting changed over here. Okay, now you can tune your this thing also. You can change the priority also over here. Okay, you can change the cost also. Okay, you can change the cost also. Understood?
Got it.
Okay. Now you can configure, change the timers also. Like the default timer, hello timer is 2 seconds and max haste timer is 20 seconds and forward delay timer is your 15 seconds. So you can change these timers also. So configure, you can configure the it should not wait for 20 seconds before you can say transition to the forwarding state. Okay, or if the switch do not hear a configuration message within 10 seconds, they should attempt reconfiguration or something. So you can change the timers also. So what I will do, I'll change the timers on the switches. So to change the timers, I need to say spanning tree. I can change the timer for VLAN 1 to 409. Any, either I can change it for one VLAN, or if I want to change it for all the VLANs, I can give it in this way. For VLAN 1 to 4094, the timers will be, I can say, hello timer. I'm not having the timer option over here. I'm not having the timer option over here. The command will be something like this. Hello timers. And I can give any timer. Suppose 3 seconds. I make it as 2 to 3. Okay, so I can change it from 2 to 3. Ah. Hey, the admin page is not coming. The page is not coming up.
Ito manos mga word.
Don't know whether there is some issue with the VM or there is some issue with the browser or something. Every time I need to restart the laptop.
Actually, this issue happens with me too when I'm trying to run Eve. I don't know why it happens.
Yeah, whenever I make the laptop in sleep mode and I just go like this only. Okay, so again and again this thing happened with me. Always I need to restart my laptop. It's not getting open, neither EVNG, neither this thing. So these are viral images which will take some time to boot up. Take some 5 minutes or something to come up.
Hi, Qayyum, Pawan this side. How can we access viral images? Can you share viral images?
Actually, I'm not having. I got it from my, you can say my one of the colleague. But right now, see, you can search this images. Okay, Cisco iOS VL2
Yeah, it's not really
15.2.
available. It's not available.
Yeah, this one and this one. Then you can import it from here. You can import. There is something in import option. Like you can add a new template over here and you can just add it to the wherever you want, either the GNS server or the extension, or you want to create any new template. You can add it from, you can add it over here. Okay, you can add a new template, then next, then here you can select the template what you want. Okay, here you will get the option to select the files. Okay, where the files are there, you will select the option and it will get installed. So this takes some time to get up. Okay, enable. I've only connected one link. So I'll just show you how to change the root path, root cost and all these things. Show spanning tree. Okay. Show spanning tree. Now config t spanning tree cost. Sorry, on the interface I need to give the cost command. Interface gigabit 0/0 spanning tree cost. I can make the cost 100. Spanning tree cost is 100. Okay, on the other switch also, other side also, 150 spanning tree interface gigabit 0/0 spanning tree cost is 100. See, the cost got changed over here on 0/0. The cost got 100 over here. Now I can change the port priority also. To change the port priority, you need to say spanning tree port priority or port spanning tree on the interface. Sorry, interface gigabit 0/0 spanning tree port priority. I can set it between 0 to 254 in the increment of 32. So I'll set it as 32 port priority. Okay. Show spanning tree. See, the port priority became over here as 32. So like this, I can change the values. This means you are tuning the spanning tree protocol. Understood? Any questions? Okay. So we'll stop over here for today.